Let's consider a couple of different functions here. Um, here's set A, and here's set B. And let's suppose we have something that looks like this. And let's call this function f. And let's have the same sets over here. Let's put another dot over here. Okay, so we have 3 elements in A, we have 4 elements in B, and let's draw this one over here. Let's have it look like this. And let's call this G. So over here we have F that maps A to B. And over here we have G that maps A to B. Now remember, for something to be a function, it has to be the case that when we look at the domain, it only gets mapped to one point over in the range, okay? And we can see that both F and G do this. But there's something very different about G than there is F. Notice that what happens over here, we have 2 different points that got mapped to the same point over here. In other words, why don't we come over here and call this A1, and why don't we call this A2, A3, here's B1, B2, B3, and there's B4. We have a very interesting situation over here. We note that f of A1 is equal to B1, and we also note that f of A2 is equal to B1. In other words, what we have here is we have that f of A1 is equal to f of A2, but A1 doesn't equal A2. Okay? Now over here, we have A1, A2, A3, B1, B2, B3, and B4. And we notice that over here, that elements from the domain just went to single elements over into the range. In other words, over here, I would say the following: if f of x is equal to f of y, then x equals y. Okay, this statement over here is not true for this function, but it is true for that function. And this is a very special situation over here. In this case, we would say G is 1-to-1. And sometimes that is abbreviated this way. Okay, let's consider some examples here. Okay, you may recall before we had a function f that mapped the real numbers to the real numbers. And we said something like the following. We said y was equal to f of x. And I don't remember exactly what we used last time, but let's make up a new example here. We'll say it's 2x plus 1. Now again, you should recognize that as the equation of a line. For example, if I come over here, f of 1 is equal to 2 times 1 plus 1, which is equal to 3. So that tells us if we were going to draw a picture of this, that 1, 3 is on the graph of this. If I were to come over here and look at f of 2, that's equal to 2 times 2 plus 1 is equal to 5, which tells me that the point 2, 5 is on the graph. And if I were to come over here and graph this thing, we know it's a straight line. We have 2 points determine a line. So if I come over here, why don't we say that's 1, 2, 3, 1, 2, 3, 4, 5. So 1, 3 is on the line. So 1, 3 would be right over there. And we know that 2, 5 is on the line. So that would be right there. And I come over here and I try to draw a straight line. It looks something like that. I think you have the idea. And the question is, f 1 to 1? Well, the way that I would approach this is the following. Suppose that f of a is equal to f of b. Then I would have f of a is equal to 2 times a, and I would have that f of b is equal to 2 times b plus 1. Well, if f of a is equal to f of b, then 2a plus 1 is equal to 2b plus 1. And that is true if and only if 2a is equal to 2b. And that is true if and only if a equals b. So our conclusion is that f is 1 to 1. Let's consider another example. Again, I want to consider some g that maps the real numbers to the real numbers. And let's suppose that g of x is equal to x squared. Now maybe you all know what this looks like already. A couple of things we note here. G of 0 is 0 squared is 0. So that means that the point 0, 0 is on the graph. And if I were to look at g of 1, that's equal to 1 squared is equal to 1, which tells me that the point 1, 1 is on the graph. G of 2 is equal to 2 squared is equal to 4, which means that the point 2, 4 is on the graph. But now let's start sticking in some negative numbers. Suppose I were to look at g of minus 1. Well, that's equal to minus 1 squared, which is equal to 1, which means that the point 1 minus 1, whoops, my mistake. That actually means that the point minus 1, 1 is on the graph. And we notice right away, look at this over here. Okay, we have the fact that g of minus 1 is equal to g of 1 is equal to 1. So in this case, look at what happens there. I have that two different values went to the same value, but these are different. Our conclusion is it's not 1 to 1. And in fact, if we come over here and we draw this, you may remember this looks like this is called a parabola. It looks something like this. And then on this side, it also looks like this. And it turns out if we're looking at functions that are mapping real numbers to real numbers, you may recall before we had what we called the vertical line test to determine if something was a function. We said that if you drew a vertical line anywhere, it should only intersect the picture or the graph just once. For testing for 1 to 1, we have what's called the horizontal line test. And for it to be 1 to 1, it has to be the case that wherever I draw a horizontal line, it should only hit the graph once. And notice over here, it's hitting it twice. In other words, we have the same y value right here that corresponds to this x value here and this x value right over here. See, if we go back and look at our last example, right over here, okay, in this case we had the equation of a straight line, you notice that wherever I draw a horizontal line, it only hits the graph once. So this is 1 to 1. Okay, so again, let's consider, here's a set A, and here's a set B, and let's consider a function from A to B. And let's draw some lines. So I come over here and I draw a line, and let's come up here and we'll draw that one. And we'll draw that one. And again, let's come over here. Again, here's A. And here's B. But notice that F was not 1 to 1. And here's G. That's also mapping A to B. But let's make this one 1 to 1. So let's have this one go over to here. Let's have this one go over to here. And let's have this one go over to here. So this one over here, this is 1 to 1. Now, what we want to talk about now is we want to talk about what are called inverses. So in this case, we're going to talk about f minus 1. And what that does is that goes from B to A. And likewise over here, I'm going to talk about g of minus 1. And that also goes from B to A. And the question we want to ask here When is the inverse a function? Now, the first question is you may wonder, well, what do we mean by the inverse? Well, it turns out, for example, if we come over here and we were to ask what is the inverse of this point here, it would be both of these points. The inverse of this point here would be this point here. So again, if we came over here and we labeled the points A1, A2, A3, and we talked about B1, B2, and B3, and we were to come down here and we were to say, what is F minus 1 of B1? Well, in this case, note that it's actually two values here. It's actually A1 and A2. Okay? So I think you can see where we're going with this. The answer is, when is the inverse a function? And the answer is when the function is 1 to 1. Okay, clearly the inverse is here. Again, A1, A2, A3, B1, B2, B3. We can see over here that for any one of these points in B, that the inverse is well-defined. And remember what well-defined means. It means that it gives you back a single value. It doesn't give you back multiple values like this one here, or it doesn't give you back no values like this one here. In this situation over here, each one of these points goes back to a unique point right over here. So I hope you can see that it's kind of obvious that if I were to calculate F inverse of F of A, in this situation, that's kind of weird, because F of A takes us to B1, and then B1, the inverse, takes us back to A1, A2. But in this situation over here, if I were to ask you what is G to the minus 1 of G of A, 1, well, that's just equal to A1. Okay? It basically took us from here to here, back to here. All right. Again, I want to consider, here's a set A. Here's a set B. And again, let's just keep it simple. We have 3 points here. We have 3 points here. And let's again draw diagrams here to indicate functions. Let's call this F. And let's come over here. Here's A. Here's B. Let's put another point in here like this. No, let's leave this the way it is. Now it looks like we're talking about one-to-one functions here. Let's call this G. And we recognize the fact that this is one-to-one, and we recognize that this one isn't. But this has another very important property over here. And I'm going to just come right out and say it. I'm going to say for any b that is contained in set B, there exists at least one A such that G of A is equal to B. And what we're going to say is if this condition holds, we say G is onto B. In other words, I come over here and I note that in the set B, there is a point here that no point in A goes to. So F is not onto. In this situation over here, G is onto. Okay, let's consider even another situation here. Here's a set. Here's a set. So let's send this point to here. And let's also send this point to here. Let's send this middle point over to here, and let's send these 2 points to here. Okay, and again, let's call this F. Now, in this situation over here, F is not 1-to-1. And we can see that because I have 2 points over here that are going to this single point. Similarly, I have 2 points over here that are going to this point right over here. Okay, so it's not to 1, it's not 1-to-1, but F is onto. Clear? Again, let's go back to our friend the line. So let's consider F that maps the real numbers to the real numbers, and let's suppose that we were to say that y is equal to f of x is equal to 2x plus 1. Okay, and I think we remember what that looks like. Looks something like this. And the question is F onto? Well, how do we show that? Well, what I want to do, remember this is the domain, this is the range. I say pick any value from the range. So I'm going to call it a lowercase r from the range. Okay, if it helps you think about this a little bit, come over here and just say r is equal to 10. Well, if it's the range, then that means that r is equal to 2x plus 1, which means that r minus 1 is equal to 2x, which means that r minus 1 divided by 2 is equal to x. Okay, remember, this is a real number. A real number minus 1 is a real number. A real number minus 1 all divided by 2 is a real number. So if I come over here and I look at f of r minus 1 over 2, well, according to our definition over here, that's going to equal 2 times r minus 1 over 2 plus 1. Well, that's equal to, well, the 2's are going to cancel each other out. That's equal to r minus 1 plus 1 is equal to r. And notice I can do this for any real number I like. So the point is that this is onto. Another way of saying that is it's saying, look, come over here to any value on the y-axis you like. So I come over here. There's a value on the y-axis. And now, again, I can draw a horizontal line. And the question is does that intersect the graph of this function? And the answer is sure, because remember, this thing goes for infinity, goes on infinitely in both directions, and we can see that absolutely it does hit it. Okay, and I can do that for any value here on the y-axis. So we can make actually a fairly general statement here, which is that any linear functions, anything of the form mx plus b, that is clearly onto R. But let's go back and look at one more example that we had before. And again, this was G, which was mapping R to R. And we said let G of x equal x squared. Now you may recall we drew a picture of that. And we said it was a parabola. It looks something like this. And the question is, G onto R? And the answer is no. For example, if I come over here, and again, I draw my horizontal line, I ask the question, does this intersect anywhere over here? And the answer is no. Now, we could come over here and define a new set here. I could say, I'm going to give this a special name. I'm going to have R plus. And I'm going to say, let this equal to the set of all x such that x is contained in R and x is greater than or equal to 0. And now I could say, well, why don't I define G this way? And I ask, why don't we give this a different name? We'll call it G prime. And the question is G prime onto? And the answer to this is yes. Okay? But we can see over here it's not onto R.